In this video about real sequences, I will explain mathematical induction, which is an important proof technique that is not specific to real sequences but will be useful for the remainder of this course. Mathematical induction is like the domino effect. If the first tile falls and each tile pushes the next one, the tiles will fall one after the other indefinitely. Mathematical induction uses this principle to prove certain properties. Let Pn be a property that depends on a natural number n. For example, Pn could be tile number n falls. The steps of a proof by induction are the following. 1. We check that P0 is true, in other words, that the first tile falls. And 2. For any natural number n greater than or equal to 0, we assume that Pn is true and prove that Pn plus 1 is also true. This means we prove that if a tile falls, it pushes the next. Step 1 is called the base case, and step 2 the induction step. After completing these two steps, we can conclude that Pn is true for all natural number n. Wait a minute. How come we assume that Pn is true when this is what we want to prove? The answer is that there are two completely different things. On one side there is, for all integer n, Pn is true, meaning all the tiles fall, which is our final target. On the other side we have, for all integer n, Pn implies Pn plus 1, which means that if a tile falls, it causes the next one to fall. This does not necessarily mean that the tile number n falls. More generally, by saying that A implies B, we are not saying that A is true or that B is true. We are just saying that if ever A is true, then B is also true, or the implication is true. In the case of dominoes, we do not need to push a tile to see if it causes the next one to fall. All we need to prove is that the tiles are close enough so that the implication and therefore the induction step is satisfied. If the first tile falls and the distance between the tiles is small, then all the tiles fall. Or, more formally, P0 and for all n in n, Pn implies Pn plus 1 together imply that for all n in n, Pn. I'm going to give you a few special examples to help you better understand mathematical induction. In the first example, the property Pn is 2 to the power of n is greater than or equal to n plus 5. Let's do the induction step first. You can hit pause and think for a moment. Pn plus 1 is the property 2 to the power of n plus 1 is greater than or equal to n plus 6. Now if Pn is true, meaning if 2 to the power of n is greater than or equal to n plus 5, we can multiply by 2 and we will have 2 to the n plus 1 greater than or equal to 2n plus 10, which is always greater than n plus 6, and we get 2 to the n plus 1 greater than or equal to n plus 6, which is exactly Pn plus 1. The induction step is therefore valid for any natural number. The domino tiles are close to each other. However, neither P0, P1, nor P2 is true. Hit pause and check it by yourself. The property is true only starting from 3. The base case here is 3. Adding the induction step, we conclude that Pn is true only for n greater than or equal to 3. Tiles 0, 1, and 2 remain upright. The others fall one after the other starting from 3. In the second example, the property Pn is n belongs to R minus Q. That is, n is an irrational number. If n is not rational, then adding 1 won't make the result rational, and n plus 1 would also be irrational. So Pn does imply Pn plus 1. The induction step is well satisfied. So the single integer that decides to turn irrational will make all the following integers irrational too. But this is not the case, and the statement is obviously not true. The domino tiles are close to each other, but none of them falls. This example shows the difference between the truthfulness of the statement itself and the truthfulness of the implication. The property of the following example is 2 to the n greater than or equal to 5n minus 8. The statement holds for all n, but the proof by induction is not straightforward. Let's try to see if Pn implies Pn plus 1 for all n. You can pause the video and think. If 2 to the n is greater than or equal to 5n minus 8, we can multiply by 2, and we get 2 to the n plus 1 greater than or equal to 10n minus 16. Is this greater than 5n minus 3? Only if n is greater than or equal to 3. This means that the induction step is true only starting from 3. In other words, the distance between the tiles is small enough only starting from 3. We check that P3 holds and use the induction step to prove the statement for higher integers. However, cases 0, 1, and 2 must be checked separately. Each of the first 3 tiles falls without pushing the next one. The last example is the most special. In this example, P is n plus 1 greater than or equal to 2 to the power of n minus 4. We start with the induction step. As usual, at this point, I suggest hitting pause and thinking for a moment. If n plus 1 is greater than or equal to 2 to the n minus 4, we add 1 to both sides. We get n plus 2 greater than or equal to 1 plus 2 to the n minus 4. Is this greater than 2 to the n minus 3? Only if n is less than or equal to 4. This means that the induction step is true only up to 4. But P0 is true, so P1 is also true. Then P2, P3, and P4. Since the induction step is valid at 4, it can also be used to deduce P5, but we cannot go further. Yet the statement holds for 6 and 7 as well. They can be checked separately, but they cannot be inferred by induction. Starting from 8, the property is no longer true. It can even be shown that this opposite is true starting from 8, which is a task you can do for yourself as an exercise. Summary of this example: tiles 0 to 5 are close enough, so the fall of tile 0 causes the others to fall. Tiles 6 and 7 fall by themselves, and starting from 8, the tiles remain upright. This is the end of this video about mathematical induction. I hope you enjoyed it, and see you in the next video.